Are you interested in space science and technology? I'm going to be showing you step by step how to create an application to design the nozzle of a rocket engine to produce a specific amount of force and reach a specified Mach number at the exit. I'll be going over all the principles of fluid mechanics, compressible flow, rocket propulsion, and nozzles, so you will get a complete understanding of how to create this app in any framework of your choice. You will be able to view the nozzle parameters, how long it is, how big the area ratio is. So for your projects, you can easily use this tool to design your own engines. Let's start. This app will allow us to design a nozzle by using the method of characteristics. So over here is the app itself. It'll be a GUI, meaning you can interactively input values and then use like a UI template to create the whole nozzle and then plot the points. We can also output all the points to a text file like shown here, because you can get the XY values from there and then also process the Mach number, the flow angle, and the Prandtl-Meyer angle at each point. I will explain this in detail if you're not familiar with rocket propulsion, since this video is intended for beginners. So to start off with, we have the first page of the app here. You can either input the exit Mach number and the specific heat ratio, or you can input all these parameters here, in which case the exit Mach number will be determined from this and then set. You can also choose the number of characteristic lines that you want and the nozzle radius. We need to know how big the nozzle will be, so to do that you need to enter the radius at the start here, and then all these points will be then determined from this benchmark. You can then see the nozzle parameters down there. We have the number of characteristic points, the maximum wall angle, the wall angle divisions, the points on the center line, those on the wall, and then the length along with the area ratio. Again, I will explain all this in detail as we go along in this lecture. So let's continue. So we have a rocket engine nozzle here. This is a quick recap of rocket propulsion. We have high pressure fuel and oxidizer inside of a combustion chamber, stored at a very high temperature as well. When the engine starts, you have acceleration of fluid moving this way, achieving a supersonic Mach number at the nozzle exit and a sonic Mach number at the middle here. So over here Mach equals 1, and then down here Mach will be some value more than 1. To design rocket engines, engineers use the asymptotic flow relations because this lets you determine pressure, temperature, velocities at different points along the nozzle itself. To start off with, we have the ratio between the temperature and the pressure. So you can find the temperature or pressure at any 2 points given the previous value and the specific heat ratio here, which is gamma. For then, you can move on to ideal expansion, where if the pressure at the exit is equal to the pressure outside, then you'll have ideal expansion. Remember that if it is lower, then it'll be under expanded, and if it is higher, it'll be over expanded. The force from the engine will be mass dot velocity at the exit, which is over here, multiplied by the difference in pressure times the area here. So AE is this exit area there. The velocity at the throat, which is over here, is 2 gamma R Tc divided by gamma plus 1. So Tc is the chamber temperature, R is the ideal gas constant. It'll be either like 355 or 274 based on what your gas is. And then gamma plus 1 is your specific heat ratio plus 1. The throat temperature is given by this formula here. The throat pressure again, and then the exit velocity, this one will be used to determine the exit Mach number, because Mach is the ratio of velocity divided by the speed of sound. To determine the exit velocity, you need to get the exit pressure first. You know what the chamber pressure is already because that's a parameter. You just divide the two and then you go from there. RTC is again this value here. The speed of sound is square root of gamma RT, and the exit temperature can be determined from this method here, using this. So moving on. let's recap compressible fluid mechanics and how things work before jumping into the method of characteristics, because I want you to understand this in full detail at the end. Let's say if you have a fluid moving along a wall and the wall turns like this, okay? So let's say the wall is turning like that. You will have a shock wave. In a shock wave, the flow slows down, the pressure increases, the density also increases, and so does the temperature. If you have a flow expansion where the wall is increasing in the area because you have a convex corner, the flow speeds up, the density goes down, the pressure and the temperature, they both go down. In a nozzle, you will have expansions. So that's why this will be more important for our application. You have something called the Prandtl-Meyer expansion function, which tells you the angle of expansion at a given Mach number. So how much the flow should be expanded by to produce this number here. So we have nu of m is equal to gamma plus 1 over gamma minus 1 a tan of this thing, Mach square minus 1 and minus a tan, this expression here. So m is any Mach number. If you see a graph of how it works for different values of gamma, so this is for some value of gamma, this one and this one here, you see how the graph is like that, because the Mach number can be any value more than 1. Since if it is less than 1, this square root will be not valid. So it's only for supersonic flows or sonic. The nu starts at 0 for all gamma. So for no matter what gamma you have, your flow will always be 0 angle for expansion. Okay, so moving on to that, let's now jump into characteristic lines and what they represent and how we will use this to design our nozzle. So let's say that you have a flow moving, right? You have a fluid moving at some angle. So let's say if that's your fluid here with some angle with respect to the horizontal plane, which is theta, as you can see here, you will have two lines of characteristics. One is left running and one is right running. The angle will be mu, which is a sine 1 over m. So this value here is a sine of 1 over m. And then once again, it'll be minus a sine 1 over m for the minus sign here. So the slope of this line will be theta plus mu. The slope of this line here will be theta minus mu. That is the same as saying for the left running values, the slope is theta minus the Prandtl-Meyer function at this Mach number. For the right running, which is over here, it'll be theta plus nu at m. So this Mach number here, which is the speed of the flow, you just substitute that into this one, and then you get this nu value here. So this nu is the Prandtl-Meyer function at m. If we have two lines which are intersecting, so let's say if you have a flow moving like this, and they both are obviously supersonic, which they must be, theta 1, which is at point 1, plus nu 1, so this one here, is equal to theta plus nu at point 3. And it's plus because you have the right running is going down here, so it'll be plus. So you see how this comes from here. For the left running, it'll be at minus from point 2 and point 3, which is over here. Just need to extend this arrow to there. Yeah, so you see how this makes sense, and then you can then get the flow angle and the Prandtl-Meyer at the third point over here, and then solve for that. So we'll be using this in our algorithm, but I hope you understood this concept here because this is the backbone of everything else. For any flow which is supersonic, you will have a positive and a negative characteristic line, which is given by this nu angle, which is a sine 1 over m arc sine. And then if you have 2 points where the flow is going up and down and they intersect, you can then find the angle of the flow along with the Prandtl-Meyer angle at that point by using these relations here. So moving on from that, you need to actually determine this point, right? So you need to actually get the slope because you need to find the xy value. So for that, it'll be given by theta 1 minus nu 1, which is of c minus here, which is this line here, plus theta 3 minus nu 3 over 2. You're essentially taking the average of point 1 and point 3 to get the slope of this line, because if you think about it logically, the line intersects both these points, so you need to average it out, right? Similar for the c plus, which is this one here, it'll be theta 2 plus theta and it's plus because we have a positive. The slope is theta plus mu at that point. And this again is a sine 1 over m. Can't draw there, but let me just like make it very clear. So a sine 1 over m, okay? That's new here. So you need to actually get the Mach number to figure out this new, because it's a sine 1 over m, right? And you can get the Mach number from the Prandtl-Meyer angle, from this value. Because remember, this is a function of m, so you need to solve backwards to get Mach. Okay, so this is most of the principles of the characteristic lines for compressible fluid mechanics. And we can now move on from here. So how can you apply this for a nozzle, right? If you have a wall, which is like this, if you have a wave reflecting, if you have flow coming in, it'll be bounce and then it'll bounce again. But if we bend the wall very slightly like this, so we have this angle here, then the wave can actually cancel out. You won't have this wave anymore. So for rocket nozzles, if you, let's say I'll break this up here. So normally when you design a supersonic nozzle, you have two sections, expansion and straightening. So expansion is where the angle actually expands from 0 to the maximum wall angle, and then it straightens out. But for rocket engines, because you want to save material, we don't need this section here. This is not needed because you're wasting material, right? Like if you build a nozzle, then you're building a metallic structure and you want to make it lightweight, you want to save space, you want to save area, and you want to reduce price. So to do that, you just look at this part here, the straightening section. For rocket engines, you just do that. Since again, you want to save money, save material, and then save time. Okay, so moving on from that, we can then move on to the nozzle design procedure. So from this, these parameters of your chamber, you can get the exit Mach number. You actually don't need rust. I took it out for the app because you don't need it per se. You just need chamber pressure, temperature, altitude, heat coefficient, gas constant, and your nozzle radius. From that, you can get all these values here, get the Mach number, and then go on from there. The parameters for your MOC algorithm is the specific heat coefficient, the design exit Mach number, and the nozzle radius. So that's why if you see here on the first page, I gave you two options because you only need these values and this one here to move on. And these values are optional. You don't actually need it. But depending on your design case, you may have this. You may not know the exit Mach number. So you have to determine it from that and then do it. So yeah, you can choose either one. Okay, I want to prove to you that the maximum wall angle, which is if you have a nozzle like this, the maximum wall angle is this angle here. At the start, if you take a tangent, it'll be this angle. It's the angle which the nozzle starts off at. Because you see how it's like it comes down to 0. This angle here will be 0 at the exit. But at the start, it's the theta max angle here. And the value for this is the Prandtl-Meyer function at the exit Mach number divided by 2. And I'll prove that to you now here. I want you to imagine point A, point D, point C, and point E. So point E is the exit, point A is the top here, D is the bottom, and then C is the middle point. The radius is RT here. So the exit at Mach, this will be the Mach number at the exit, right? ME. Okay. Remember I said that the angle is a sine 1 over m, that's mu. So that'll be this angle here. And remember I said that before, if we have a characteristic line going like this, then we can say that theta A plus nu A is equal to theta C plus nu C, which is this line here. So what's theta C? It's 0, right? Because at the middle of the nozzle, the flow is going that straight. It's not moving anywhere. Over here, the flow is at an angle. Because you need to imagine fluid moving in this nozzle, right? You will have like fuel moving very fast here. So at the middle, it'll be 0 because it's going straight. But over here, the wall is there, so it'll be going in this direction here. So if I draw arrows, it'll make more sense to you. And new A is, we don't know that, but I'll show you the trick here. So we can get this expression here. Theta A is theta max because the flow is moving at the wall angle. It's moving tangent to the wall essentially, right? And the wall starts off at theta max. So the flow is moving this way, which is theta max. So yeah, we have this expression here. We can also say that theta C minus new C, because we have a left running characteristic line here. And I'll just quickly recap that if you missed it, which is this one here. So theta minus new at point C is equal to that at point T because these two intersect. Theta E is 0 because again the flow is moving straight here. It starts off at the wall angle and then goes straight to 0. So we have that there. Theta C is also 0, right? So what does this tell you? MC equals ME. The Mach number here is the same as the Mach number there. Now this might be kind of mind-blowing, but if you look at rockets, the Mach number isn't the same over here. Like the Mach number actually reaches the exit Mach number much before the nozzle exit. And it is a bit tricky to understand, but because of these whole characteristic line mechanism, the Mach number actually reaches here and is the same over there. So the Mach number all the way here is the same as at this point. Now we need to actually do one more thing. We need to look at point D to C. So we have this line here, which is again a left. It's a left running characteristic. So theta minus nu at D is at point C. Again, C is 0. And then theta minus nu at D is equal to C. But think about how the nozzle is symmetric, right? The nozzle is the same here as there. So nu A is equal to nu D because the flow is moving at the same speed here and here. Because it's the same nozzle, it's symmetric along this line here. So with that, theta max equals nu C plus nu D, which is nu A plus nu D. And then you can get theta max is equal to nu C divided by 2. Because we add this here, and then you get nu C plus nu D, and then nu D is equal to nu A, right? So if we sum these two expressions here, you will get that is theta max is equal to nu C. So 2 theta max is nu C because this will cancel out and then it will be added by 2. So we get theta max is equal to nu C over 2. So the flow, the maximum wall angle is equal to the flow Prandtl-Meyer angle at the Mach number at the exit divided by 2. So since nu C is the same as nu E, then this will be nu at ME divided by 2. Okay, so moving on, we can then characterize our nozzle by the number of characteristic lines. So if you have 2, you will have one line here, one line there, and then you will have one reflection and then a second reflection. So we can say we have points 1, 2, 3, 4, and 5. Where they intersect is very important because you need to actually determine the Mach number there. So now let's say if you have 4 lines, right? We have 1, 2, 3, 4, 5, 6 to 9, 10 to 12, 13 to 14. If you have 6 lines, we have 1 to 7, 8 to 13, and so on. Can you see a pattern? So let's say if you have 2 lines, right? You see how it goes from 1 to 2 plus 1, then 4 to like this value plus n. So value here is like, there is a pattern in this this whole solution, right? If you look at n equals 4, it'll be more clear to you. So let's say 1 to 5, that's the spacing of n. 6 to 9 is the second reflection, so we have n minus 1. The spacing between this is n minus 1, right? If you have 5 minus 1, that's 4. As we move along the nozzle, it goes down and down. So 10 to 12 and then 13 to 14. So similarly here, if you have 1 to 7, that's 1 to n plus 1. Then we have this plus 1 and then 2n. So this like spacing here is n plus 1. And then if you add that to n, you get 13 plus n minus 1, 18, n minus 2, 22, n minus 3, 25. And then lastly, n minus 4, which is like 2 here, it's 27. So do you see a pattern here? Like, do you see how we can actually determine the number of points from this n here, the number of lines. So n is the number of lines here. We need to determine how many points we have in our nozzle, and then which are the wall points. So by just knowing this, since you have a pattern, you can actually get both of these variables from that. If you add this up here, if you add this way backwards, you see how for the last one, it's always 2. There's only 2 points. So at the last characteristic line, there's only 2 points. We have the center line and the wall directly. There's no intermittent points. So we can say that it always starts off at 2. Okay. So then we have what? 2 plus 3 plus 4. We just keep going up and up until n plus 1. So we just keep adding numbers starting at 2 and going all the way till n plus 1 here. So we have 2 plus 3 plus 4. The last value is n plus 1. The last value is n plus 1 here. If you recall your math class, this is a classic sequences and series case. If you have an infinite sequence where it goes from 2 plus 3 plus n plus 1, this is simply n times n plus 1 over 2 minus 1. Because since we're starting at 2, we're not starting at 1, we need to subtract the 1 there. Because if you have a series like 1 plus 2 plus 3 plus 4 and so on till n, for n numbers, it'll be n times n plus 1 over 2. But since we're starting at 2, we need to subtract the 1 from that. And this n plus 1 will carry over here. So the number of points are n plus n times n plus 1 over 2. So you can directly get this, how many points you have from how many lines you need. We have 1 to n plus 1, so that's a wall point. That's a wall point. It's spaced out, so it starts off at n plus 1, then goes to n. Then if we add n minus 1, we get the next wall point. If you just look at this picture, you'll see the pattern. Because over here we have n plus 1, then we have one less point in the middle. So we have 2n and then n minus 1, n minus 2. We just keep going. So that's how you can get all the wall points. You just start off with this and you keep on looping it. In my algorithm, I do this in detail, so you will see it then if you don't quite grasp it here. Okay, first characteristic line. We need to start off at point 1. We're at point T here. Let's zoom into it. Point T, point A. Now, why do we do this? Why do we imagine a point here, A? And why do we just do that? Because look, if we start off at point T itself, over there the MOC equals 1. Remember, the MOC is sonic at the throat, right, of a nozzle. So the panel Mayer angle is 0. So you cannot solve anything here because you will have this as 0 and then you won't have a solution to this one because this needs to be a non-zero value. So we need to kick off the angle a bit. So we need to initiate the algorithm from a small angle. So for this one, I chose 0.19 degrees. If we look at these 2 points, you see how the slope is going up because it is increasing, the flow increases here. Now, you might be thinking that the flow angle of theta A, which is this flow, is the wall angle. But it's actually not because the wall angle is a bit after. We assume that the wall actually starts a bit after point A. So the wall angle is downstream a bit. It's not at here. Because if we do assume that this angle is the wall angle, then MA will be too high, right? It'll be an insane value because it should not be the case. It should be slightly larger than point T. So it should be let's say 1.02 or something. It can be 1.5. So we assume that the throat is slightly extended prior to the expansion. So prior to the wall angle starting, we assume that there is a small extension. Okay, now, and this is done because we cannot have a starting at Mach 1. We just cannot do it because then the angle is 0 and then you won't have any solutions. Okay, so from that, we can say that theta T equals nu T is equal to theta A minus nu A. Since theta T is 0, it's not, the throat is going straight before the expansion. It's going straight before. And then theta is nu A. I choose a small theta A, 0.19 degrees, and then I get nu, and I get my Mach number from the panel Mayer expansion. And then from point A, we can then start off, okay, getting 0.1. Theta A plus nu A is theta 1 plus 0.1 because this is like this here, we have a downward sloping line. And again, this comes from, I'll remind you guys one more time, it comes from here. This expression. You get new 1 and then you go from there. So theta 1 is 0. Why? Because the flow at the middle of the nozzle, your x-axis is the nozzle's center line. The new 1, you need to get it. Now imagine if I had used point T instead of point A. What would be the case? These two would be 0 and then new 1 would be 0. So you will be stuck in an infinite loop, right? So did you understand why why when you design a nozzle, you need to kick off the angle a bit? Because if you start off at point T here, if this was point T instead of point A, then these two would be 0 and then you won't have any solution for new 1. You will be stuck at Mach 0 here. But does that make any sense? No. That's why you need to kind of initiate the angle from a small angle and then move on to point 1. So I hope that makes sense. And then you get new 1, you get M1 here. And then you get the mu angle, which is 73.6, which is A sine 1 over M. So you get this from that. So let's read that one here. Yeah, you get that. Now what is the slope of this line here? That comes from here, right? This one, 0.1, 0.3, you just divide them. I'm doing the same exact thing here. Point A, 0.1, you just get the average, you get minus 75.23. So this angle here is minus 75.2. So from this angle and this, you know what this value is. That's your nozzle radius, right? So you just get 0.1 by using geometry. So yeah, you have 0.1 now. And let's move on to 0.2. I just want you to look at this one here. We call this one here, if we add two lines and then one going down, one going up, you can get this angle and the Prandtl-Meyer angle. So for 0.2, we have theta A plus nu A minus theta 1 minus nu 1, which is from this, because we have one downward sloping here. Okay. You get nu 2. Okay, anyway, I'll show it now. So it gives us nu 2 is equal to 0.38 because look, that's 0. Nu 1 we just got it before here. These two are known. We pick it ourselves, 0.19. So we get nu 2 is equal to nu 1. We get this is the same as this. But what does that mean, right? It means M2 is M1. But can you do that? No, that's not possible. The Mach number must be more than M1. Why? Because we're going downstream. The Mach number at this line should be less than the one here because we're moving along the nozzle, right? The flow should be speeding up, but it's not happening. So did you see what the problem is? So that's our first issue of doing this here. And don't worry, I will explain the solution in a bit. M2 should exceed M1. I hope you got that because we need to move along the nozzle and get the points. Let's say we got M2 is equal to M1, okay? Now let's find the third point. So which is this one here. We have one line like this. Let me just draw it better. And then 0.3. So then let's move on, right? So nu 3 is equal to theta A plus nu A minus theta 2 minus nu 2 divided by 2. And this value is interpolated, and I'll tell you after how you can get it. So don't worry about it now. I want you to calculate this. You will get a value nu 3 is less than 0. But that's bad. What would the Mach number be if it's less than 0? It's undefined. Because recall, in the Prandtl-Meyer function, it has to exceed 1, the Mach number. It can be less than 1. So yeah, like we're kind of screwed because we're stuck here. Like we have an invalid solution. So that's it for the video, guys. Thank you for watching. Alright, I'm just joking. Yeah, I'll get to the part in a bit. So we have a problem. We're stuck at no answer. So we need to fix it. And what I'm about to tell you next is very important. So pay attention. Okay, there is a trick to this. What you do is you you go to point A and you zoom in even more. And what you have to do is you need to get point 2 and point 3 from not point A. You need to get it from A to A3, like these imaginary points here. We can assume that their XY location is at point A, okay? So we can assume that they lie on point A, but the flow angle is a bit different. So you'll see how that works. So theta A minus nu is equal to theta A2 minus nu A2. This line here. And then again, from A2 to A3, theta minus nu again, formula. So theta AX, so this 2 can be any number here. This always holds, okay? Because this is always 0. So these two cancel out because we just did it, right? This from our assumption that we kick off a small angle, and then from point T, which is at 0, you get these two the same. So this leads to here, where now these two are the same. And then again, since these two are the same, if we subtract them, then these two will be the same, right? Because it's 0 here. So then you see how this expression is true. It always holds. You find point 2. I will tell you now. For point 2, you assume that again it's at A2 and A3. You don't know. You don't know this yet, right? You don't know these yet. And you also don't know nu 2. What do you do for the first set of reflections? So let's say, for example, for these points here, and for these points, the first reflection, you need to do interpolation. You assign a value to nu 2 by interpolation. You know this angle is 0. This is, you know what this is, nu 1.38. No matter what you do, there will always be a valid theta A2, nu A2, which satisfies this formula here. Okay? Because if you think about it, if you add two numbers which are the same value and it's divided by 2, like if you have, let's say, x plus y divided by 2 is equal to some value n, no matter what the value of n is, you will always have a valid x and y, right? It's just math. So we can move on. From interpolation, I chose nu 2 is equal to 1.19, and then you can backward solve for theta A2 and nu A2, because remember, right? This is 1.19 times 2, that's 2.38 minus 0.38, which is nu 1 here, that's 2. And then since these two are the same, you divide by 2, you get 1 each. So from this, you can get M2 and then the MOC angle. You can then get this theta x, which is again, we have this line here, 1 to 2. You add them and get their average again from here, from this one here. You get that. You can also get theta x2 from this. Since we have a downward sloping, you get this and then you get 0.2. Because we need to know this angle and this angle to get 0.2, right? Because we have a line coming like this and a line going like that. We need to know where they intersect. So you get it. And then you just keep moving on. At each point, you must find this theta ax and then m and then mu, and then you just get each point. So for point 4, you will have this. So you just go on from point 3 and then you just get them all. So that's your first reflection done. You can keep doing this until you get to the first reflection, like the wall point. This angle will be what? It'll be the maximum wall angle. So we just keep on going from there. And then at the last one, after theta 6, you extend this out to 7 to be the wall angle because it's the first section. And then these two will match. These two are parallel lines here. The last is parallel with the wall. So you see how for the first reflection in this example in the lecture, they both are the same. The theta and the nu, they're the same because these both are got by interpolation, right? You can get MOC and then you can get the slope and then you can just move on from there. Now let's move on to the remaining part of it. Now for the next part, you don't need to do any interpolation, because now look, for point 8, we don't look at point A, we look at point 2 because it's starting from here, right? So we look at point 2 and then we look at point 1. Then we have theta plus nu is equal to theta plus nu at point 2 and point 8. You can again get all this here like before. Get theta 2 8. Get M9, nu 9. Get this angle here from before. For 10, it will be like this. You use 0.4 and 0.9. For 11, you use 0.5 and 0.10 because we'll have 1 point here. So we can do an algorithm like this and we can keep going until we solve them all. So this is our logic flow. We start off with these 2 points here, get the maximum wall angle, which I proved to you how you get it. You break up theta max into n divisions from theta max to 0, theta array. Get the number of points, get the wall points, also get the centerline points too. First section, you need to do this offset thing where it is like interpolation, because again, I told you why, because of this major issue we had. You have to do this offset stuff here. You do interpolation, you get theta 2 backward solve, and then you obtain all the points. Then for the remaining points, you use the points from the previous section, get all the others. And the wall angle, you see how it goes down to 0. So we'll have maximum wall angle, and then we'll have a smaller one, and then it'll be to 0 eventually. So theta array I, because we need to do interpolation. And I will show you after how I did the interpolation, okay? So yeah. For our algorithm and our app, again, you can use any programming language you want to use. We'll be using object-oriented concepts for this. And I will explain it in such a way that no matter if you're using C++, Java, Python, like even TypeScript, JavaScript, HTML, CSS, you can all do it using the same logic here. So we have a bunch of classes we need to use. The first one is equations. Return outside temperature and pressure. Get the exit Mach number. Get the PM angle. Get the Mach from the PM. So backward solve nu from M. Interpolate the angle. N is the number of lines. Vector to string, and then return XY point. This one we'll use all the time to get the XY points. So to get all these points here. Let's look at the terminology. TC, chamber temperature, Mach number, pressure, specific heat ratio, gas constant, number of divisions to break up theta into, the number of lines, characteristic lines. This N and this N is the same. Theta is an angle. XT, YT, and theta are slopes, points and slopes. Panel mirror angle is nu. Nozzle radius, number of points. NL, number of lines. So this N, same as this one here. Exit sound speed, maximum wall angle. For the engine class, you will have initialized points and then reset, because in our app, you can update it in real time. So you can do it. For the engine, we will have all these parameters in there. And we will have an array of points. Each array will be a point object. And this will be the number of points, right? Because each point has a bunch of values. Index, like we need to know the Mach number, we need to know the XY location. So for each point, you will have index, flow angle, panel mirror angle, XY location, Mach angle. Is it a wall point and is it a point? So we will use these booleans to actually progress with our algorithm. So now let's move on to the app itself. So for my app, I'm going to be making it in C++ and Qt. Now, again, it doesn't matter, but for me, I do like to use C++ a lot. So Qt lets you plot things and make GUIs from C++. So to start off with, let's look at the backend. You need to have a bunch of classes. The first one is the engine class. Let's look at that here. We have the point class included within the engine class because you will have a vector of points. So the constructor is the engine itself. You have two methods, initialize points and reset. And then you have all the class variables. Now I know in C++ you should make them private because you need to use methods to get them and set them, but I wanted to save time here, so I just use public variables. Obviously, in the industry, you can't do this. It has to be private. You need to use proper coding standards, but I just wanted to do this for demonstration. You will eventually end up with the same thing. So we have chamber pressure, temperature, specific heat ratio, R gas, gas constant. I put the units at the side for reference, nozzle throat radius, number of points and lines. Then I have my exit pressure, temperature, sound speed, Mach, wall angle. And then this one here is an array. So if you use JavaScript, you will have to use a different notation, but this is an array of points, right? I'm making an array of my characteristic points because you will have many points and I need to represent them somehow. So I put them into an array. Now you can use a hash table or anything else, but I feel like an array for this is quite useful because you can iterate in the array and then you can solve each point, its XY location, Mach number, is it a wall point, and so on, right? So I would strongly recommend use an array for this. And C point is each point in my nozzle, my characteristic point. So let's now look at that. I have index, flow angle, panel mirror angle, Mach number, the Mach angle, which is A sine 1 over M, XY location, and I have two booleans. Is it a wall location and is it a centerline location? So it'll be one or none of them. It can be both. And my constructor, I can make one. I can directly pass in my index and then go from there. So let's look at the methods of the engine class because that's quite interesting. I have two methods. Let's look at the first one, reset. Let's look at this simple one here. In my reset method, all I do is I reset my vector of characteristic points. I clear the vector. Why? Because every time I change my parameters, like let's say I want more characteristic lines, I need to recalculate everything, right? You can't just like assume things from the start. You need to reset the whole thing. So I just clear the array. That's my array, which is this one here. And I just clear it. I start from scratch essentially. And then I have my initialize characteristic points. The first thing I do is get the number of points from the formula which you saw in the lecture, n plus n times n plus 1 over 2. And then I start. So I make my vector, I make each point, C point, point I. I check if it should be a wall point or not. So what I'm doing in here is, remember I told you the spacing, I had n plus 1 and then it was like n, then you add n minus 1. I'm just doing that here. I'm just going along and then I'm saying, if it is a wall location, then set it to true. So here, my first point at index 1 is on the center line. So I need to set that to location here. And if my point is on the center line, in the middle, on the x-axis, my flow angle is 0. So if something is on the x-axis, the y value will also be 0, right? And the flow angle. So these two will be 0 here. Again, if it is a wall location, if the previous is on the wall, the next is on the center line. If you look at this picture here, you see how when I go to point 8, point 7 is the center line. So all I have to do for that is if my previous point is on the wall, the next point is on the center line. So all I do is if at I minus 1 index, which is in this for loop here, this big for loop, if something is on the wall, the previous point, the new one will be on the center line, right? And then again, my flow angle is 0 and the y location is 0. I have two loops here. The first one gets the wall points. The next one gets the points on the center line. The wall points are a bit more tricky. So all I do is I do the n plus 1 thing. So I say k equals 0. J is 1 plus n lines. So 1 plus n. And then I say if it is on the wall, I increment k by 1 and then I increment j by j plus n lines minus k, because you see how it goes from n plus 1 to n minus 1. So I need to do the plus 1, minus 1, minus 2. I need to do that, right? So I do that like this here. So n lines minus k become n lines minus 1. And then again, it'll become k plus 1, n lines minus 2. And I'll keep on going along the wall here. Once I have all the wall points, I can very easily find my centerline point. So like it's best to first get all the points on the wall and then you make a second loop, and then you check. If it is 0.1, it'll be by default on the middle. So any nozzle you have, the first point is always on a center line because you start from there, right? So that'll be a center line, and then again, I check if the previous point was on the wall, the new one will be on the center line. So that's how I get my whole points, and then I can set them right now itself. Okay, so moving on, we have equations class. So let's move on to the methods here. I have return outside temperature and pressure, get exit mark, PM angle, mark from PM, interpolate angle. And then I have these two here. Now this is specific to C++. You may not have to do this in Java. I'm just making a vector to a string. So I have a vector of numbers. I want to make it a vector of strings because I want to show it in my app. So I will need to do that here. And then I have a second one for integers. Then I have my last one to get XY point. So in C++, if you want to represent two values, X and Y, you can use something called a pair. Instead of using an array of size 2, a pair is more neat, it's more like friendly, because if you have a pair, you get the value by saying pair dot first and then pair dot second, instead of like using arrays and doing indexing. So once again, it's best to use a pair if you want to return 2 points in C++. Okay, so we have the top point, X and Y, the top angle, the bottom, and then this bottom angle here. So let's now go into these methods here. To get the temperature and the pressure outside, all I do is pass in my height, and then I use the International Standard Atmospheric Model and then get my pressure and temperature from that. So these can be found anywhere online. To get the exit mark, I'm passing in pointers here because I want to actually do a check. If my specific heat ratio is less than 1, I make it 1.4 because again, the specific heat ratio must exceed 1, otherwise it'll be invalid. I make it 1.4 because for air it's normally that, so it's a good default. Also with my pressure ratio, the flow must be expanding, right? So the pressure must be going down. So by accident, let's say if you incorrectly set a value, it'll become false, and then I will have a default case. Set to 0.4 here. And then I reset my chamber pressure. So the pressure at the exit is found from this one. If you recall, I had optimum expansion, so the pressure exit must equal the pressure outside. So from this, I get my pressure ratio, I get my exit temperature, sound speed, velocity, and Mach number. So these are again the isentropic flow relations. To get the PM angle, I just substitute my Mach number and my gamma into the Prandtl-Meyer function here, and then I get my angle. And if gamma is less than 1, I just default to 0 to prevent any errors, because I don't want to solve this if that's less than 1, because it'll be invalid. To get the Mach from the PM, I'm backward solving. So this is a fixed point iteration. I'm essentially just solving it backwards. If you look at the picture, it makes sense to you. I check if my Mach is less than 15. I think 15 is quite a good upper limit. I get my residual value. If it's less than 0.0001, I exit, because then I've found a good solution to it. Or I just increment this, and then I'll go back to here and then solve it. So this is a very simple way of solving an equation for an unknown backwards. Okay. I then have my angle interpolation. So for here, I just take the decimal point of the angle and then I break it up into divisions. So I'm just saying that if my angle here has some decimal point, it'll take it into consideration. And then I just get my temporary value. I break it up into divisions, a delta, and then I just increment along there, okay? And then I get my vector. So that's my vector, which I return. So this result has all the angles interpolated. And then I will use it for my actual MOC algorithm. I then have my vector to string. So I just make a vector into a string here, quite simple, by using toString in C++. And then after, I have my XY point here. So for this one, it is simply done by geometry. If I have a point on the top and the bottom, and if I have two lines which slope down and slope up, I know what their angles are. I can easily find the third point by just doing a geometry. And then I return that point. So again, all these methods can be done in any language. I've showed you a generic case. Since C++ is quite low level, you should be able to do this in a simpler way by using MATLAB or Python. So I've shown you the most like detailed case. So I hope that helps. So I think that should be it for the backend, right? We have my characteristic point, and then I just have my initializers. I set both to false, wall or centerline, because I don't know yet, right? I need to actually check for it. So initially make them false. For Q custom plot, now this you can get from online. That just to plot my results. It's specific to C++, so I won't explain it here. I will show you in the app how I use it. Okay, let's move on to the rest of the app. I have two windows. The first one is my main window, where I set my values. Now, if you have not used Qt, you can learn this yourself, how to make a GUI. It's actually very easy. You can just draw widgets and then do it. So like I won't explain it here, but it should be quite straightforward. If you just look like online somewhere. And I have my blank app here. So I have like this here. I have set up the whole thing. I have two input fields here. And all these are input fields. So all these will be a string. I need to make it into a float after. Okay, let's move on to the actual app itself now. The actual implementation of it, the front end, and how it interacts with the back end. So in my main, I just opened the main window, so that's by default. Okay, here. I have my main window.header file. I need to include my backend. My backend is in my source folder, src, so I include that here. And then if I go into my main class, I just get the value. So now, since the user has two options, they can either put the Mach number itself or the chamber pressure and all that stuff. I do it like so. Again, I won't go over like all this syntax here because then we'll be here all day, but this project will be on my GitHub, so you can take a detailed look at it there. I have some like exception handling and like basic GUI stuff really. Again, if you use like JavaScript or Electron or TypeScript, whichever you want to use, you can use basic GUI design to actually create something like this. I then pass the engine class to my next page. So in my main class, I make an instance like object of the engine. If you see here, this engine is there. Okay. I then take my engine object and pass it to my next class because I need to go to the next page. So I just pass my engine like that to my new class, which is the second page here of my GUI itself. So I just pass it in like this. I include engine there. And then you just make an engine object. So this is when I pass it from main. I make a new page and then I send the object there, and then that's it. So now I'm on my second page where I actually do the MOC algorithm. Over here you can see the entire procedure for the method of characteristics. With an example, we have 4 lines and 14 points. The first thing you do is you reset the engine. You set the number of points and the number of lines. So that's for 14 and 4 in this case respectively. You then initialize the characteristic points, which tells you which ones lie on the center line, in this case 1, 6, 10, and 13, which ones are on the wall 5, 9, 12, and 14. You can set these from this one method here. Get the maximum wall angle. You break up into divisions. You pass the number of lines. You pass 4 into this here. It'll be a size 4 array. So you interpolate the angle in that interpolation method. You get the wall points and the center points. So in this case, you need to search this array. And if you remember this array, each element in the array is a characteristic point, and that point had two attributes, right? It had the booleans, is point on wall and is point on center line. So you search the array and you mark the points which lie on the wall and the center. You set the engine throat radius. You initialize theta A and nu A, which was that small angle. In my lecture, it was 0.19 degrees, and in the example too. So I used that, and then I got my Mach number along with the Mach angle. You can then proceed with setting point number 1, as I showed you in the lecture, where you have point A, you know the slope. You can use a tangent and then do it. Pretty simple. Then you proceed with the next reflection. So the first reflection here, points 2 to 5, because you need to do the interpolation for theta and nu at x, imaginary point here, which is somewhere up there. So you get the left and the right running slopes. You get the xy locations of these points here. When you get to point number 5, you need to extend point 4 up, and then this will be the maximum wall angle. You solve for x and y at point 5. When that's done, you have the first reflection. You can get all the remaining points with this. Now, before I move on, I want you to look at this pattern here. Do you notice something? For point 6, I use point 1 and 2. What's 2? It's 6 minus 4. For point 7, I use point 6 and 3. So that's 7 minus 4 and 7 minus 1. For point 8, I use points 4 and 7. That's 8 minus 1 and 8 minus 4. For points 10, what am I using? I'm using 10 minus 4, that's 6 here. And then, but if you look at this one, it is 10 minus 3, it's 7. You see how it's going down by 1, the increment? So here it's 7 minus n, that's 4, 8 minus n. Here it's 10 minus n minus 1. So that's 10 minus 3. And then here it's 11 minus 3 here. So n minus 1. And for point 13, it is n minus 2. So 13 minus 2, that's 11. So you see how the subtraction goes down by 1? And you will need to know that for the algorithm. So I get my Prandtl-Meyer angle, Mach number, Mach angle from the connecting previous point, which is here, this one here. For point 6, I'm using point 2. I get my left slope. The right slope is 0 because I'm at point 1. It's going straight. Remember, if it is on the center line, the right slope is 0 because you're going straight, and then you get the xy location. If it is not on the center line and not on the wall, so here 0.7 and 8, you get the division angle by interpolation. You start off at index 1, okay, but not 0 because the angle here is 0, but the angle here is not 0. It's from the first element of this array here. You get that, you get the new Mach and the angle from the previous point. You then get both the left and the right slope from the points of contact. So when I say points of contact, I mean for point 7, it'll be 3 and 6. For point 8, it'll be 4 and 7, okay? With these two, their slopes, and you already know what their xy locations are because you solved for them before. You can get the new xy location of 0.7 and 8. Number 9, since it is on the wall, you set the flow angle, Prandtl-Meyer angle, Mach number, Mach angle to the previous location. So for 9, it'll be at 8. You set this property the same. You then get this angles again. So you set the left slope to the previous flow direction angle. Solve for the right slope at the bottom contact point. And then get the xy location. So you solve for the slopes from the bottom location. That is 8 here. The left slope, that'll be the wall angle interpolation. So it'll be like -1. It'll be an angle smaller than the maximum wall angle. And you see how it goes to 0 eventually. Then you get the xy location of the wall, of location 9. When you do that, you need to reset a few things. You reset the index of the flow assignment back to 1, which is this one here. Just move it out the way. So you reset it back to 1. And you increment the counter, which is used to get the previous contact point, which is needed for this here. So like for point 11, it is 11 minus 4 minus 1. So I'm incrementing that counter. That is pretty much the entire algorithm itself. If you didn't find it super clear, when you see the app and how I did it there, you will again reinforce this concept. It is more of a visual explanation instead of a text on a screen because you need to understand where each point is located respect to the others and how you can actually design the entire nozzle based on interpolation and finding slopes and angles. It is quite an extensive process. That is why I had my two classes for the engine and the equations to help me solve it faster. It is best to use object-oriented programming for this. Now let's jump into how I did it in the app. Over here is the algorithm inside of my app. The app will compute all the points and load them on the screen. So I reset. I get my number of lines by converting the text in the field to an integer. This field is this one over here. I then get my number of points by initializing the characteristic points, the maximum wall angle, the interpolation here. I search the array for the wall points and my center points. By using vectors, I push back into my array if it is a wall location and if it is a center line location respectively. I then have two conversions for radians to degrees and degrees to rad because I want all my angles to be in degrees for display. It's a lot easier to understand. My point A, I have my XA, theta A, slope A, because these numbers I got from the 0.20 degrees I had used as my small angle approximation. I then compute my 0.1 over here by setting the x location a tangent to it and then get the angle, Mach number and the Mach angle, a sine 1 over m here. To get the Mach number, I use the get Mach from Parnell-Mayer method, pass in my Mach number originally, which is 1, pass the Parnell-Mayer angle and the gamma, the specific heat ratio, and then I can continue with the rest of the algorithm. So if it is a wall location, I have my theta divisions, that is my interpolation, that's my flow angle here. Get the Parnell-Mayer angle, the first reflection, they are the same. I get the Mach number and the Mach angle. And then I do the theta AX and nu AX approximation here. So you see how I solve for my theta AX. It's twice the interpolated angle plus nu at I minus 1, the previous point, minus the Parnell-Mayer angle. So that's theta minus nu divided by 2. If you look at the formula in my lecture, it matches up with this one here. I get my Mach number, I get my Mach angle. I find my left and right running characteristic lines by using the formulas. For left running and right running, it's a bit different. You have to subtract instead of adding. So just, if you look at the formula and if you look at this, they all match up again. The flow angle is my value for the direction of my flow where it's going. The nu is the Parnell-Mayer angle here. And this value here, mu, is sine, a sine 1 over m, okay? So when I have that, I get my xy location of point I and then assign it to my first and my second. I then extend it to my wall location here. So I just extend out the angle here, and then you see how I set the flow angle, the Parnell-Mayer angle, the Mach number and the Mach angle to the one at the last point here. Because it's the same angle, right? It's tangent. The lines are parallel. When I have that, I find my top and bottom slopes. And then lastly, I get the wall location. So from lines 65 to 104, that's my first reflection on the first point. So when that's done, I can get the remaining points. I check if it is a center line. If it is not a center line and not a wall location, if it's an intermediate point, I basically find the PM angle, Mach number, and then it's a very repetitive process, but I just do it here. I get the slopes, top and bottom. If it's on the center line, the bottom slope is 0. So I can then get my XY intersection point here. And you see this I minus engine copy dot n lines minus j. That is the connecting point, right? Because it's, I told you before, it is minus n at the start and then you go down by 1. This j here is my counter, which I need to increment after. I'll show you that in a second. So I just pass in my x location, y location, and then the xy at the bottom point and the bottom slope. So it's quite a big method, but that is how it's done. The next thing I do is also find the location if it's on the wall. So extend my flow angle here and then get the top and the bottom slopes from, again, the formulas, and then return the XY point and then pass it in. Last thing I do is reset K to 1. So that's my index for the interpolated angle divisions, theta div. Then J plus equal to 1 is to get my connecting point, because that decrements by n minus 1 each time you go up a reflection. So that is it for the algorithm itself. If you get stuck, just look at this in more detail from my repo in GitHub, and then if you just have the formula breakdown at the side and all the equations on one page, and if you look at this at the same time, you can mix and match. You can match the formula with the correct line here, and then you will see it a lot better. So that is practically it for the app itself. And now let's run the app and see what we get. Just before that, the methods here are just to plot the values. I'm using Q custom plot syntax. I don't stress too much about this because you don't have to understand it fully. As long as you just look through this method, you'll get it. The last thing I do is output to a file. I just output all the points, XY location, the Mach number, the flow angle, the Prandtl-Meyer angle. So let's begin and let's see a demo of this app. Okay, we can now begin our application. If you want to try this application for yourself, you need to have C++ installed and also Qt Creator. I'll provide the links below for that. I'm using C++ 17. It should work on that. So that's my project file here. To open the app, just download the repo and open this PRO file, .pro, Rocket Design App. Make sure you have print support here for the plotting. Inside the source file, I have all the files that I need for my backend and the Q custom plot to make my graph. Before you run the app for yourself, you need to change one thing here. So go into method of characteristics.cpp and change this path of the output to the path which you want. So in my case, I want the text file to output to my desktop, so I just used it. But you need to go to your folder wherever you want it to output and paste that directory here. So this is in my name now because you need to change it. Make sure you do this before you start the app because otherwise you'll get an error. So yeah. Now let's run it. To do that, click this run button here. And we see the app has opened up. Let's try option 2. Directly set the Mach number. I'm going to use 2 and 1.4. I'm going to use 4 lines and my radius has 35 centimeters. We can see that the nozzle is created. We have 5 points along the wall. It starts off here. And if you zoom in, we can actually drag and zoom in here, so it's interactive. We can see each point calculated. And next step is, if I go in my desktop folder, I have my nozzle here. Now for you, this will be somewhere else based on wherever you set that directory to. So if I open this, I'll see everything here. I had something open, so I'm just going to delete these lines at the bottom. So yeah, I forgot to reload the file, but I have 14 points and these are the 14 of them. So let's try some more, right? Let me actually delete this here. Every time you rerun, you should delete what's in the file here. And then let's try 9 lines, right? So now we see it, the graph has reset. We have more accurate divisions. The interpolations can be seen here. These are the points on my center line, the nozzle wall. I have my nozzle length and the area ratio. You will see that this area ratio goes down the more lines you have. So if I have like 12, it'll drop more. It's becoming more accurate. The more lines you have, the more accurate your shape is. If I just had like 4, it's a lot higher. That's not good. And let me just delete what's in this file again and reset it. So let me try the maximum limit. I have 45 lines. You see it's a lot more accurate. I have 1,000 points here, so it's quite detailed. I have all these points along the wall and center line, and these are all my interpolations. Now you can't see them all because the field is cropped off, but if you extend it, then you should see it. But let's open this points here. Let's see what we have. So we have all these points here. We have the Mach number given to us here everywhere. So the Mach at the exit is about 1.93, which is pretty accurate. It's close to 2. We have the flow and the Prandtl-Meyer angle here. So it looks quite nice. Let me just zoom in back there. That's your nozzle, and It looks quite cool, right? You see it changing in real time. That's the benefit of using a GUI. You can see things update very quickly. Let me again reset this. And now let's try something else. So let me restart the app. This time I'll do all this here. So let me set the pressure as 2.276, the temperature as 1500 Kelvin, altitude is like 4500 meters, specific heat ratio I'll choose 1.55, and my gas constant as 355. Again, these parameters can be up to you. Make sure that they are realistic though, otherwise you'll just get errors. Now if I do all this, I cannot set anything here because the field is blanked, because you cannot do it, right? You can choose one or the other. So press continue. My Mach number is 3.05. So you see it calculates it from the get Mach and then the backend here. So let me try, let's say 25 lines, and my nozzle radius as 50 centimeters. I'll make it big. So that's my nozzle there. I have a much larger area ratio, 9.8. I have my nozzle is much longer, 600 centimeters. It's like 6 meters, it's like massive, right? It won't be actually this big in real life. So I can also do a reset. But before that, let me open the graph here. You see the Mach at the exit is 2.92. It's quite accurate. Now let me delete this and let me try a new value. If I just put 5 lines, right? You see it's a lot less accurate. It's more jagged, the wall. And now if I do it, the Mach is much more inaccurate. It's 3.67, but that's much higher than the design Mach number. So the more lines you add, the more accuracy you get. Let's say 25 and let's try 15. So now you have 10. Area ratio 10.2. So yeah, now it's a lot more accurate to the design now here. So that is it pretty much for the video. I do recommend you download this app for yourself and try it out. It should be pretty fun, and I hope you learned a lot. I know this video was very long, but be sure to leave a like and subscribe if you enjoyed the content. I'll make more like this in the future. And with that being said, I'll see you in the next video. Bye.